Okay, last time I taught this particular concept, I also introduced a concept on what is called significant digits. And significant digits is a mathematical thing that we need to do when we do calculations dealing with numbers. Excuse me. I haven't had to deal with significant digits so far in this course because we've really only done 2 or 3 calculations. We calculated the weighted atomic average for the isotopes. I think we might have calculated one other thing, but the rest of it's been theoretical. But now we're getting into some mathematical stuff. And last time I taught it, I took half the lesson to teach about significant digits, and I didn't think that that was a useful way of doing that. Now, I do have a video that I made when I talked about significant digits, and it is there. So as I teach you and as I go through calculations, I'm going to teach you as I go how we do proper rounding, all right, mathematically. There is, like I said, a handout on today's date for significant digits with the rules on how you do this proper rounding. There's also a little video. The handout looks like those 2 big white pages over at the back that says rules for significant figures in a measured quantity, along with what is an exact number, etc., etc. And so like I said, I'm not going to teach that as an official lesson. I'm going to integrate it into when we do our calculations. If you want to know more, if you're concerned more about how we round, come and see me or see the video, or, you know, there are many ways you can learn more about significant digits. Just do a Google search for rules for significant figures or significant digits, and that'll be covered. So I'm going to just continue on and teach this, and I'll integrate the significant figures lesson into it. All right. So that deals with calculations. Now let's talk about the chemical concept that I want to talk about today, and that's something called the mole. Now, the mole obviously describes a small furry creature which burrows in the ground and doesn't see very well, but in this case, mole is a shortened version of molecule, all right? And it deals with the way chemists count atoms and molecules and ions, something that we defined the other day as entities, right? Remember, I defined those little things that chemists deal with as being entities. So when we want to count entities, really small chemical things, we need to count them in big numbers. And that's because we can't see individual molecules, atoms, ions, but we can put them in really big numbers or really big piles, and then we can see it because there's a lot of it there, right? So we need a way in which we can count these things. All right. Don't write this whole thing down. Let's just be a little critical about what we're going to write down. You've already got the title. Let me read it through first, and I'll tell you what I want to write down. Atoms, molecules, formula units, and ions are too small to see. Observable changes in these chemical reactions must involve extremely large numbers of entities. So when I generate hydrogen for a hydrogen balloon, and I get a balloon full of hydrogen, there are billions and billions and billions of atoms in there. So in order to see some hydrogen in a balloon, we're talking about massive numbers of atoms, or molecules, H2 molecules. Therefore, we need a method for counting large numbers of entities and measuring their mass. The unit that was chosen was the mole. You know what? I like this whole thing. Let's write the whole thing. I've changed my mind. Write the whole thing down because it does give us information about all the important things. The first one reminds us of our entities, the things that are small that we want to deal with as chemists. This jacket thing's pretty slick, though. I don't know if I could get used to it or not. It's pretty warm. Warmer than a lab coat. I got to go with the shirt collar out past the jacket a little bit. Is that the look? No? Sure. All right. I don't know. I feel like George Stroumboulopoulos on Hockey Night in Canada. Which I hate, by the way. Bring back Don McLean. I love that. Observable changes in chemical reactions must involve extremely large numbers. And that's an important thing as well. When we're dealing with something that you can see, if you get a glass of water, there are billions and billions and billions of water molecules in there. So how do we count these large things? Well, we put them in really big groups. Just like if you're counting eggs, we typically don't count individual eggs. What do we count eggs by, typically? Yep, dozens of eggs. That's not a really big number. I guess it's a handy number. So the mole is essentially a really big number. It's like a dozen, except it's like supersized. It's huge. A dozen is useful for counting eggs. If you have a dozen dozens, like if you have a dozen pencils in a box of pencils, and then you get a box of boxes that have a dozen of them, that gets you 144. Does anybody know what that grouping is called? That grouping of numbers, if you have a dozen dozens. It's not used very often. It's called a gross. Have you ever heard that before? No? A gross is a dozen dozens, right? A ream of paper. You know, if you get a stack of paper, you buy a pack of it, right, at, say, Staples. It's called a ream. That has 500 in it, so a ream is 500. I believe Google itself is a numerical value. It's a really big number. I think it's 10 to the exponent 10 or something like that, right? So we've got all kinds of different grouping numbers, but this number, the mole, is specially designed for chemistry, right? It's not just a big number, but it's a very specially chosen number. It's actually a calculated number. Chemists have calculated the value for this large group that we call the mole. All right? So what I want to do today is I want to tell you what that really big number is, and then I want to tell you how we're going to use that really big number in order to do some mathematics. All right, so the mole, let's click on here. So there is the term, 1 mole of any, you're writing this all down. So 1 mole of any substance contains Avogadro's number of entities. So the mole is the unit. The number itself has a name. It's called Avogadro's number, and it's named after the chemist. He was an Italian chemist. I think lived around the time of Sir Isaac Newton. No, a little later. Actually quite a bit later, maybe about 100 years later. It doesn't matter. And he proposed a rule, a law, that dealt with the way gases behave. We're going to learn this law at the end of the course. It's called Avogadro's law. And eventually, other chemists, using that law, were able to do mathematics to determine the value of this number. And again, it's not just any old big number. It's not like a Google, 10 to the exponent 10. It's a very specific number, 6.02 times 10 to the 23. All right? So it's a very, very specific number. So there's the number itself. If we then call it the mole, 1 mole contains 6.02 times 10 to the 23 things, entities. We can have moles of ions, moles of molecules, moles of atoms. All right? Now the unit for the mole is mole. And then we shorten that down to mole. Let me explain what I'm talking about there. Let me just change the screen here, and I'll bring this back for a moment. Let me just bring it over to here so I can write some stuff down. All right. Let me just go through some units to give you an idea where this unit comes from. In science, we have what we call the SI units. There are standard units that we use. So if I'm talking about something like length, and you don't have to write this down, length. In other words, this is the quantity that we're measuring, quantity, all right? And then we have a unit for all of these things, and then we have essentially the symbol for that particular unit. So if I'm talking about length, what do we measure length in? If you're taking physics, you use this unit. What do we measure length in? Don't be shy. Share it with me. Joel, you've taken physics. What do we measure length in? Meters. Meters is correct. So we write that down as a meter, and the symbol is M, right? And we can use all of our metric prefixes with that. So we can have kilometers, and we can have centimeters, and we can have micrometers, and we can have all of those things, right? And so that's the standard unit for length. If we're dealing with mass, now this is a little tricky. Physicists like to use not the standard unit, they like to use something else. But what's the base unit for mass? What do we measure mass in using the metric system? Joel? Grams. A gram, and its symbol is G, all right? And time. Time is another very important thing when it deals with physics and chemistry and stuff like that. And does anybody know what the metric unit for time is? The simplest unit for time. This is a tricky one, yep. Yeah, it is the second. It's not hours, it's the second. The second, all right? And its symbol is S. And with all of these SI units, we can use our prefixes. So we can have kilograms, and we can have micrograms, and all of those SI systems, or all of those prefixes, they're on your periodic table. Actually, take a look at the data sheet of your periodic table so we can have a look at those things in a moment. So I'm looking at the data sheet, and in the table at the top, you'll see all of those prefixes, because we're going to have to use them eventually. So you should be able to see that kilo. What does kilo stand for? Actually, I'm going to leave one more space here, and down here I want to write down some of these things. What does kilo stand for? What does the prefix kilo represent? It's just right there. All you got to do is read it off. Yep. Kilo is 100. What is it? It's 1,000. What does it say right on that page, though? It doesn't say 1,000, I believe. Read it off exactly as it is. K is 10 to the power of 3, which is 1,000, right? So the symbol K represents 10 to the exponent 3, all right? So if I have kilometers, I have 10 to the exponent 3 meters, or 1,000 meters, all right? And let's just pick some others. How about centi? What does centi represent? Yep. Well, C is the symbol, and it represents times 10 to the power of negative 2. So it means times 10 to the negative 2, all right? So I can have centigrams. We don't use that very much. Milli times 10 to the negative 3. We use that one a lot. We can even use micro. It's pretty small. It's times 10 to the negative, what's micro? Times 10 to the negative 6. So that's really tiny. So we can have microseconds times 10 to the negative 6, 1/millionth of a second, right? We can have micrograms, very tiny little masses. Micrograms would be something that we wouldn't even use in daily life. Milligrams, right? If somebody's taking some medicine, the medicine is usually measured in milligrams, right? If you take a regular Tylenol or a regular Advil, it's usually something like 200 milligrams of whatever the chemical is. So we've got length, we've got mass, we've got time. The last thing that the SI system has is what we would call quantity. Quantity. In other words, you're counting things. How to count things? Just by counting them in numbers. And the SI unit for counting things is the mole. All right? We have the mole is the official way in which scientists count things. Now, they only really count little things. Atoms, ions, formula units, molecules. But the SI unit is the mole. Notice we've got meter, gram, second, M, G, S. And so what's the symbol for mole? Well, it's MOL. What did we do? We got rid of the E. Wow, that's quite a condensing of the name. We're too lazy to write the E for some reason. But that's the official symbol for mole. So when we write down a unit, when we count moles, we write MOL. All right? Now, it's just like the rest of them. So I can have millimoles. I can have times 10 to the minus 3 moles. And I can have kilomoles, thousands of moles. All right? We'll be using the mole quite a bit over the next, well, you'll be using it for the rest of your chemistry career if you take chemistry, because it's the way you count things. And sometimes you will have a prefix associated with that. All right, let's go back and learn a little more on how we do calculations with the moles. So, the mole, a very big number of things. Before we get into calculating, though, don't write this down. We did this yesterday. This is the entities. Sometimes I write it down, not yesterday, but when we did formula units. Sometimes I write it down there. If I have Na, why is that black? That's, oh, because I picked up the black pen. If I have Na, what is the entity? If I'm counting the smallest pieces of Na, which entity am I describing? This is more of a review, I guess. Of those tiny things that I've been rattling off all class long, what is Na? Atoms. So if you have 1 mole of Na, you've got 6.02 times 10 to the 23 Na atoms. If I've got CO, carbon monoxide, if I have a mole of CO, I have 6.02 times 10 to the 3 carbon monoxide. What type of particle is CO? Yep, molecules. They're molecules. So these are molecules. If I have calcium chloride, if I have a mole of calcium chloride, 6.02 times 10 to the 23, what do we call that smallest piece? Yep, formula unit. I'm going to go straight to Ty. We're going to roll through this because I want to get to the homework. Formula unit. It's like the molecule, except it's the ionic version. And if I had a mole of SO4 minus 2 sulfates, what is that smallest piece called? Ty? It's an ion. All right? So that's what we're talking about when we talk about entities. And we have that list from the other day. I made that list. Some of you are writing it down, but hey, you can go ahead and do that. I'm likely going to jump ahead to the next slide here in a second because we already have that list. But when I use the term entities, that's what I'm talking about. Okay? All right? Okay. A little bit of information about the mole. You do not have to write this down. This is just to kind of represent how big the mole just really is. Avogadro's number is that really big number. If you had Avogadro's number of sheets of paper and they were divided into 1 million equal piles, those piles would still stretch from the Earth to the sun and probably a little bit past, not much. That's how big this number is. So whenever we talk about things that aren't those little entities, it's really absurd, right? 10 to the 23 is such a big number, we can't even begin to count things that are what we call macroscopic. That's things that we can see with our eyes. Avogadro's numbers of pennies side by side would stretch more than for 1 million light years. So if you put pennies side by side, a mole of them, it would be so far away, it'd just be unimaginable. So again, to talk about pennies in terms of, you know, a mole of them is really absurd. We don't talk in terms of that. In order to obtain Avogadro's number of grains of sand, you would need to dig up the entire surface of the Sahara Desert, which has an area slightly less than the United States, to a depth of 2 meters. So that's a big area. Then you counted all the little pieces of sand. So I guess there is, right, obviously an Avogadro's number of sand pieces on the Earth. That would be the only thing that you could hold in your hand and see that we could say that there's a mole of on the Earth. All right? The average in an average lifespan of 75 years, a person's heart beats on average, that's supposed to be a 10, that's a typo right there. On average, 2.84 times 10 to the 9 times. The total number of heartbeats in an average lifespan of the entire population would be 4.3 times 10 to the 20 heartbeats. still not a mole. So a mole is a really big number. That's all I'm trying to get across here, is that a mole is a huge number. But if I have a mole of water, it takes up 18 milliliters. In 18 milliliters of water, right, that's about the amount in like a correction fluid container, right? 18 milliliters contains a mole of water molecules. And that's what makes it useful, in that it gives us an amount of substance that we can put on a scale and that we can measure and that we can make sense out of. It's not too big for those little entities. All right, let's now do some calculations, and you are going to write this down. What I'm going to teach you in the next slide really does not necessarily have anything to do with chemistry and the mole, but it has everything to do with a method in which we solve our problems mathematically. It's a problem-solving technique. Often it's called the conversion factor method for solving problems. If you've taken physics with Mr. Petrus, but you wouldn't be taking it this term because they're doing that 3U physics right now in Mr. Petrus' room, so you wouldn't be doing it this term. But when you do, you may learn about something called the dimensional analysis method of solving problems, and dimensional analysis is the same as the conversion factor method. So if you're taking physics next semester and he starts talking about dimensional analysis, then it is the same thing. So what is a conversion factor? When one quantity is equal to another quantity, this relationship can be used or turned into a conversion factor. We can write this relationship as a ratio which can be used to convert one unit to another. Not a bad explanation, but this is the type of thing that you learn best how to do by actually seeing some calculations done. So on the next slide, I'm going to show you two types of numbers that we can deal with. One of them is inequality, and the other one is what I would call a combined unit. And both of those numbers that I'm going to show you can be used as what we call a conversion factor. So we're going to deal with one at a time here. Let's bring the slide up here. And there's both of them there. Only write down the dozen eggs for now, and then we'll worry about the kilometers an hour in a moment. And I'm going to do these left and right on the slide. You can do them above and below each other. It doesn't matter. But you'll see here that I have an equality. 1 dozen equals 12 eggs. That's the definition of what a dozen is. And it's simply an equality where we say one is equal to the other. The other unit is what I would call a combined unit. This is a velocity, this is a speed, and it combines two units of 110 kilometers per each hour, the speed of, say, a car going down the freeway. We can use both of those to generate conversion factors, which we can then use to solve problems. The possible conversion factors for 1 dozen equals 12 eggs look like this. 1 dozen per every 12 eggs. You will write that down. So all I've done is I've taken the equality and I've made a fraction out of it. I keep the units in it. Now there's another way I could have wrote this down. I could have wrote this down as 12 eggs in each dozen. and they both mean the same thing. All I've done is flipped it over, okay? Now, due to the fact that 1 dozen is equal to 12 eggs, this entire fraction is actually numerically equal to 1, because they're the same thing. A dozen is 12 eggs. And whenever you've got a fraction that has the same thing on the top and the bottom, that's actually equal to 1. So I can take that conversion factor and I can multiply it by a number and I can get a new unit out of it, but it doesn't change what it is inherently because I've really just multiplied it by 1. That doesn't do anything to it. So let's say that I have 2.0 dozen eggs. And, 2.0 dozen. And I want to know how many eggs I have. Well, this is an easy question. If I've got 2 dozen, how many eggs am I dealing with? Yep, 24. Let me show you how we get that answer using the conversion factor method. I know that I have dozens. I know that I have a conversion factor that converts dozens to eggs, and that's what I want to be able to do. I want to get rid of the unit dozen, and in the end, I want to replace it with the unit eggs. So I'm going to choose a conversion factor that has the unit dozen on the bottom. Because if I have dozen on the bottom, I can cancel out the units, just like I can cancel out a common factor in mathematics. In mathematics, if I have 4 times 2 over 2 times 7, what can I do with those 2's before I start calculating? I can cancel them out. If I choose the conversion factor that has dozens on the bottom, there it is there, it's the second one, 1 dozen equals 12 eggs, then what I can do is I can essentially cancel out the unit dozen. And in the end, what am I going to get? I'm going to get 2 times 12 divided by 1, which is 24 eggs. And you might think, wow, Mr. Sanders, that was a crazy amount of work just to multiply a number by 2. But what I'm doing there is I'm illustrating to you how this works. Let me give you an example now that isn't quite as nice. What if I have 2,752 eggs? And the question is, how many dozen is that? Now again, many of you in your mind have done calculations like this and you know exactly what to do. But when we start dealing with moles and mass numbers and grams, it's going to get confusing. So we want to come up with a way that's going to get us the right answer. Without asking some of the brainiacs out there what to do, because you guys are already thinking what to do, which is fine. I have the unit eggs. I want to get rid of the unit eggs, and I want the unit dozens in the end. I'm going to choose one of the conversion factors that's going to allow me to cancel out the unit eggs and leave me with the unit dozen. Which of the conversion factors does that? The first one or the second one? Which one's going to allow me to cancel out the unit eggs? Because I want to get rid of that unit eggs. Which conversion factor is it? Yep. 1 dozen over 12 eggs. The first one. Perfect. I see that I have eggs. I want to get rid of eggs. 12 eggs is 1 dozen. And again, some of you out there were saying, yeah, I knew we were going to divide by 12. That's great. What is the number there? What do we got for the number? Come on, share. This is all works with sharing. You got to have calculators. You got to have them right beside your hand. Right? When I finish writing down the thing, I should be deafened by the sound of little fingers clacking on the keys. All right? And then there should be arms shooting into the air like a bunch of Hermione Grangers wanting to impress the professor. What do you got? So, 229.33333. We're going to only keep 1 because I want to keep 4 significant digits. I'm going to talk about that in a little more detail. 0.3 dozen. Okay? Do we have supporters on that number? Don't just take it for, we get it right? We got it? Thumbs up? Good? All right, excellent. Good. So if I have an equality, I can turn it into conversion factors. You can do this down below. Let's talk now about the velocity one. If I have a number that's made up of a combined unit, it's got two units in it, with also the slash, which represents a division, I can also turn that into a conversion factor. 110 kilometers is how far you go. What goes on the bottom? Yep. 1 hour. It's implied, 1 hour. 110 kilometers in 1 hour. Or, what's the other version of this conversion factor? Yep. 1 hour over 110 kilometers. Excellent. So, if I'm traveling for 7.32 hours, how far will I go? Now, again, some of you are very analytical thinkers and you're just looking at the unit and you're thinking about the unit and you're just doing something. That's okay, but when we get to complicated questions, I want you to default back to this plan. Which of my conversion factors am I going to use? So the question in your mind is, well, what unit do you want to get rid of? What unit are you trying to get rid of here? Yep. Hours. So where do you want hours to be in the conversion factor that you choose? Oh my goodness gracious. That the denominator means the bottom one. She's right. Just in case some of you aren't mathy. Correct. I want it in the denominator. So I want the first one, right? I want 110 kilometers in 1 hour, and has someone done that calculation as I'm babbling away? We got a number? Number at the back? Yeah? 805.2. 805.2 kilometers. Now here's a little kind of a preview to what we call significant digits. This number has 3 significant digits. I'm going to help you on how we count those in a moment, but right now, 1, 2, 3. This one could have 2 or 3. We're going to assume it has 3. We're going to assume it's exactly 110 kilometers. 1 hour is a whole number. It's a perfect number. We mean exactly 1 hour, which means it doesn't have any significant digit. It actually has an infinite number of significant digits. Again, as we go on, I'll talk more about this. 1, 2, 3, 1, 2, 3. We're going to round this to 1, 2, 3, which means we round it to 805 kilometers. All right? So we always round it back to the number of significant digits that is the lowest in the question. And we're assuming that this one is 3. And again, I'll talk more about that in a moment as we get going. What I don't want you to be doing when we get to the end of this course is writing out your entire calculator run at the top. That is incorrect. You should always be thinking, where do I stop the number of decimals? And there is a method of determining that. Okay, so those are conversion factors. Let's now talk about Avogadro's number as a conversion factor. I should have actually addressed one thing before. I'm gonna get you to stop for a moment and back up for a moment. What can I convert between with this conversion factor that we did first? What are the 2 possibilities I can convert between? I actually did the 2 examples here. What am I able to convert between using this conversion factor? What 2 units can I convert between? Yep. That's because it's in the thing, right? I can go between dozens and eggs or eggs and dozens, right? What 2 units can I convert between for this conversion factor? Yep. Kilometers and hours. What will I be able to convert between using Avogadro's number? Yep. Moles and entities. What you can convert between is always found in the units of the conversion factor. So Avogadro's number as a conversion factor allows me to start with entities, the little tiny pieces, and put them into big piles called moles. And that's useful. You might not think it's useful yet, but it will be useful. By the way, that conversion factor is on your sheet in the constants part of it. You'll notice it says Avogadro's number. It says 6.02 times 10 to the 23, and it says ent/mole, which means if you're doing a quiz or a test and you all of a sudden freeze up and forget what that number is, you've got it there. All right? All conversion factors can be flipped over depending on what we want to find. Let's do some examples. You good to go? Good to go? So just put EG. Just put EG. You don't have to write down the conversion factors. I just put them there so that you don't have to look all over the place to find them. Later on, you're going to have to know where to find that number. You'll either have it memorized or you can get it off of the data table. So let's say we had 1.7 moles of CO. And the question is, how many entities is that? Let me do A together and then you can do B on your own. 1.7 moles of CO2. When I write mole, by the way, it's a scribbly mess. It usually looks like Knoll, but I mean mole. What's going where in my conversion factor? What's going where? Jenna doesn't get the answer because she's answered a million of them. Now we're checking other people. What's going where? Yep. And what number goes along with mole? So 1 mole on the bottom, and then obviously the other number, 6.02 times 10 to the 23. And I usually just write ent to kind of shorten up entities. Now, here comes our calculator training. This is fun. You'd be amazed how many people don't know how to use their calculators. It's kind of painful, really. And I often say if we could send text messages with our calculators, you guys would be masters of your calculators, but you can't. All right. We need to put in that scientific notation. And many people don't know how to use your calculators. Do not ever press the times button and then put in 10. Do not ever do that. And then the arrow up button and then whatever your exponent is. 6.02. Do not ever do that. There is a special button on your calculator that stands for times 10 to the. And it's either an EXP or it's an EE. If you have a Sharp calculator, you'll be looking for EXP. If you have a Casio, I believe it's an EXP. If you have a Texas Instruments, it's likely an EE, all right? And some calculators even put the button as times 10, and then it's got like a little X or something up there, or a Y or something like that. Everybody find their button? You find your button? Okay. So here's how you're putting it in. 1.7. You following along? Times 6.02. Then press the EE or EXP button. Then press 23. And then you could press divided by 1, but you really don't need to do that because dividing by 1 doesn't do anything. What answer do we get here? What answer do we get? Kayla, what do you got? Say it a little louder again. 1, exactly 1? And what do you got? Okay. 1.0234 times 10 to the 24? 24. And that is, what unit is left? After I do my calculation, what unit is left? Yep. Entities. And what is the entity for CO2? What do we call the CO2 pieces? Right. So now I have 1.0234 molecules of CO2. Now, significant digits. Significant digits come from measurement. Significant digits come from how we measured the number and what kind of measuring device we used when measuring the number. If you use a measuring device that contains lots of little tiny millimeters on it, then we can know more decimals than if we use a ruler that does not contain millimeters. Because there's lots of rulers out there that don't contain millimeters. So if I've got a ruler that contains lots of tiny little divisions, then I know more decimals when I measure using this device than when I measure using something else that contains less divisions. Every number that we present you with has either been measured or it's a whole number. In other words, it's a number that has been defined, like 1 mole. Somebody had to measure these moles of carbon dioxide, and they used a device that only measured to 1 decimal. The rest of the decimals are unknown because their device was not good enough. It didn't have enough divisions. So for this number, there are only 2 significant digits. 2 significant digits. How can we help you?
Corbin?
Corbin, he's writing my test, okay, but I think he's got lots of time. Corbin, you can come and check this out. You can go out the back door, okay? And Abby's not here. Yep. So, this number has 2 significant digits. Avogadro's number. We actually know Avogadro's number to many significant digits. We know it to about 7 or 8 significant digits. Scientists have been doing experiments and experiments in order to determine what that number is exactly. So we do know many of them. But for the case of our questions, we're going to only use 3 of those significant digits. 3 significant digits. This number 1 right here is a whole number. It means, let him back in there when he tries to sneak in that back. Not right now, he's still talking, but when he tries to sneak back in. It means that the whole number is a perfect number 1. It wasn't measured. It didn't have to be measured because it's the definition of what a mole is. It's exactly 1 mole. Being a perfect number, it means that this thing has an infinite number of significant digits. It's a perfect number, all right? It's exactly 1.0000000. When you take your answer, always round it to the least number of significant digits that are in the question. What's the least number of significant digits for all of my numbers here? What's the one that has the fewest? Nat, what is it? 2. So I'm going to round this to 2 significant digits, which then means I've got 1 and 2. I'm looking at the 2, and that's going to not round down, but stay down, right? So my answer is 1.0, let me get the yellow back, 1.0, there's my 2 significant digits, times 10 to the 24 molecules of CO2. All right? Now, I will be going through that little procedure every time we do a question. At the beginning, when I start doing quizzes and tests and things, I'm going to be checking that you're getting close to the right number of significant digits. As we move on and practice it more and more, I'm going to expect you to get better at your significant digits. If you write down the entire 9 characters on your calculator, you're going to lose marks for not thinking about significant digits. All right? because they are important. Okay, 5.67 moles of NaCl. You'll notice it's the exact same problem. I'm hoping maybe as I was babbling on, you were doing that problem already. That's awesome if you did. Again, I want to get rid of moles, 6.02 times 10 to the 23 entities. And again, you're running the calculator, 5.67 times anything that's on the top, you press the multiply button for. Anything that's on the bottom, you press the divide button for. Dividing by 1 doesn't make any sense. 6.02 EEEXP 23, needing the number. All right, what do you got there? So you would have 3.41, and then what came after? 334, but you're knowing that this is 3 significant digits and 3 significant digits, so you're going to round that and leave it. Nice job. Times 10 to the 24. And NaCl, what do we call those little entities? Yep. You're right. They're called formula units. Now, you know what? Let's say you get going and I'm asking you to do some calculations and you can't remember what to call those formula units. All right? I've had students write down FU before, and it's not very nice. You could do that. But if you just wanted to put entities of NaCl, I would accept that. I'd say, yes, you've got proper units. All right? So I'm not concerned. If you can't remember the unit, don't worry about it. If you can remember that it's molecules or atoms or ions, that's great. Okay. Let's do a couple more examples here. If you know what you're doing, by all means, crash on ahead. Let me just give you a little heads up here on this one. 4.0 times 10 to the 15. Now notice, I always rewrite the number I'm given, because I've got to start thinking about which conversion factor. Now notice in my conversion factor, I have moles and entities. This is molecules of water. What am I going to put there instead of molecules so I can think my calculation through? What is molecules an example of? Yep. Entities. So when I see molecules, I'm thinking tiny little pieces. I'm putting ent H2O. What's going where in this case? You know what? I'm hoping you're not answering me because you're all doing the problem because you know what to put where. That would be awesome. So I'm going to go back to Jenna. What do you got? So what goes on the bottom? Yep. 10 to the 23 entities per 1 mole. I cancel out the entities. And notice the unit that I have left is moles of H2O. Because the identity of the chemical itself is also a unit. It's an important little piece. So this time, it's 4.0 EEEXP 15. You don't have to actually press times 1. But for anything on the bottom, you're pressing the divided by button because we're dividing out that factor. So then it's divided by 6.02 EEEXP 23. And we're looking for a number. What do you got, Jacob?
0.0000.
Oh, and I don't want that. I would like it in scientific notation. So you can either move that decimal over, or there's a button on every one of those calculators that'll automatically turn it into scientific notation. And none of you have any idea what that button is, because the first thing you do when you get home with your new calculator is you open the box, you take out the calculator, you leave the book in the box, and then you throw the box in the garbage. But I know how to do that with every one of those calculators. And I'm willing for a fee to show you, because that's not part of my job. No, I'm joking. I'm not going to do it for a fee. Look, I'm recording this. I'm putting it on the internet. For all those people listening, I don't charge students for teaching how to use a calculator. All right. I will come around and I'll show you. Does somebody have that scientific notation? What do you got? 6.64 times 10 to the negative 9. Do we like negative 9? Supporters on the -9? Nobody's sure. You got a 1, I got a thumbs up. -9. And what's the unit? What's the unit? Yep. Of? Yeah. Moles of H2O. How many people have 0.000000006? And it stops right there. All right. And you're all going, where did they get the 6, 4, da 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 da? What's happening is your calculators typically only have 10 characters on the screen. And so when you have this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this is times 10 to the -9, your calculator is hiding those little digits. And if you get that number, if you get something that's all zeros with that, you need to find the button that turns it into scientific notation, because there are hiding digits over there. And in a moment when I'm done my other examples and I get you to work, I'm going to come around and I'm going to help you find those digits. All right? So make sure you put a little mark beside this question so I can come around and help you how to find that. Okay, let's do another calculation here and get to the end, and then I can help you out. So 5.67 times 10 to the 26 ions, so that's entities. Potassium, that's K plus. 6.02 times 10 to the 23 entities. 1 mole on the top. What do we got for that one? Somebody done it yet? Oh, you're waiting for me. Don't wait for me. If I'm babbling on about something and you think you get it, get your pencil and try it. Don't wait for me. That's how you gain confidence. That's how if you beat me to the answer, you can do a little self-pat on the back. Yeah, I got that. It's good stuff. Somebody have an answer to that one? Other than Jenna? Well, you don't know how to put you're able to put the E and EXP. You're worried about this happening again. Oh, don't worry about it. That was a fluke. You'll either have it work out nicely for you, or it'll turn it into scientific notation. Because if you have a number that's smaller than 10 to the -9, it's going to automatically turn it into scientific notation. That was a fluke. What do you got? 941. 941 moles. Yep, I like that. 3 significant digits. 3 significant digits. 1's a whole number. 3 significant digits. I like it. 941 K plus moles. All right. Do we have supporters on that? Again, I always ask everybody, make sure we check each other. We're good? We got a thumbs up? I like the thumbs up. I just want to put a couple twists on this before I leave you to do your homework, and then I'm going to come around and help people with calculator issues. Possible issues that you could have, don't know how to put in the EE or EXP. And possible other issues, how do I turn that into scientific notation? I'm going to be introducing another conversion factor here, one that is different than Avogadro's number. I'm going to be teaching you conversion factors from here to the end of the course. Now that I've taught you the conversion factor method, we're going to keep learning more conversion factors, and we're going to make the questions a little more difficult. This is the next step. So, again, always start by writing down what you have. In this case, I have 2.34 moles. Yep, moles of aluminum chloride. I need a formula for aluminum chloride. Again, I always say I have that periodic table nearby. I need an aluminum chloride. Tests are marked, by the way. Marks are up. Yep. AlCl3. Notice in this question, I want to find chloride ions. I have aluminum chloride moles. So ultimately, I need to get to entities of chloride. I can only do conversions one step at a time. So I take it one step at a time. I have mole, and I have a conversion factor that can get rid of that mole. Somebody tell me what to write where in order to get rid of that mole. Yep, Liam? Where is it? Which is on in the denominator? The mole, right? That's the bottom, right? Because I'm a little slow mathematically. You mean the bottom? Yeah, I like the bottom. 1 mole. What goes on the top? Don't say numerator or I'll lose my mind. It's okay. Times 10 to the 23. And what's the unit? Entities. So let's get rid of this and let's analyze what I have. What units are left if I do that calculation? Because I'm not done yet. Yep. Of aluminum chloride. But that's not what I want to find. I want to find how many chlorides there are. I need a new conversion factor. I can create conversion factors as long as what I put in them is a true statement. If I make up a conversion factor that isn't true, then I'm not going to get a correct answer. I need something that gets rid of this aluminum chloride and turns it into chloride ions. Eric, what would you like to do? I have 3 chlorides for 1 aluminum, that's true. But I have 3 chlorides for each aluminum chloride, right? So I've got to get rid of aluminum chloride. So where am I going to put it? I'm going to put it on the bottom. So I'm going to make a true statement about chlorides and aluminum chloride. I've got to get rid of this. So for every 1 aluminum chloride, how many chlorides are in that? Eric? 3. So I'm going to put 3 chlorides. Now that's a true statement. Where did I get it from? This 3 right here became that 3 right there. It's like I plucked off the chlorides, right? It would be like saying, right, in my hand, if we include the thumb as a finger, we're going with the thumb as a finger today. If I were to say, like, in my hand, for each hand, there are 5 fingers, right? So if I have aluminum chloride and I plucked off all the chlorides, I'd have 3 chlorides. Just like if I had my hand and I plucked off all my fingers and put them in a pile on your desk, right? I pulled them right off. There'd be 5 fingers sitting on the desk for each hand, right? That's Halloween. Isn't that a good way of thinking of it? So that's exactly where that comes from. Okay, so now we're ready to calculate. 2.34 times 6.02 times 10 to the 23 divided by 1. You don't have to press divided by 1. It just doesn't do anything. Times 3 divided by 1. Don't have to do that. You don't have to. Now, for significant digits, 3 significant digits, 3 significant digits. These are whole numbers. There is exactly 3 chlorides in each aluminum chloride. So it's not like that's a measured number. That's a number that's just true. So we don't care about those for significant digits. I'm going to round to 3 significant digits. Yep, Jenna? 4.23 times 10 to the 24. We got supporters on that? Okay? And what's my unit that's left after I've canceled everything away? What units have not been canceled away? And you're literally looking in there. You're finding it in there. Liam, what do you got? You're right, it's chloride ions. Some of you might just write entities of Cl minus, or you could write chloride ions. Okay? Now, there's another example hiding in there, but I'm going to stop there. On the worksheet that I assigned the formula mass, the next section is called the mole. And that's online, okay? You can do that section. There's also 2 questions out of the textbooks that you can do as well. All right? And the answers to these sheets are found in my PowerPoint. So again, if you go to the PowerPoint for today, you'll notice at the end of the PowerPoint here, I've got the answer to the mole section on the sheet, and you can check your answers that way. Yep. Yep, I'm going to stop the recording and get things going here, then I'm going to come around and help you guys with the calculator. So let me just stop this recording, because it's got a, oh no, what's going on here? Why is that thing choking? Recorder.